several years junior to me. We both had the same advisor. So this is kind of like a Duke reunion card. So I'm going to talk about a special situation, a special scenario in logistic regression called separation. And we're going to look at the effect of using the Cauchy prior in this case and the performance of some other priors. And we'll look at some theoretical results and some empirical results, and hopefully we'll be able to give some useful recommendations. So here is the usual notation. Y is the burden response variable. We have P predictors, x1 to xp, and we assume that the design matrix X has full column rank, and it includes the intercept in this case. And here we have the usual logistic regression model, and we're trying to look at choice of priors for the regression coefficients data. So in linear regression, the choice of priors has been well studied, and many authors have advocated against the use of normal priors. These are computationally convenient, but the problem is that the results can be sensitive to the choice of the prior variables. And so many authors have advocated the use of heavier tailed priors, and especially priors with tails like the Ghosh. And these tend to resolve some of these problems in linear regression. So less is known for logistic regression, and Andrew Gellman, in a paper in 2008 in Annals of Applied Statistics, he gave this choice here of independent Cauchy priors and regression coefficients as a default choice for logistic regression. And in general, he recommended a family of independent T priors, and Cauchy was the default choice. And before using the prior, he suggested kind of making the predictors more comparable on a comparable scale. And so he suggested centering binary predictors and standardizing numeric predictors to have mean 0 and standard deviation 0.5. And after that, he recommended this Cauchy prior with location parameter 0, scale parameter sigma j, which is 10 for the intercept and 2.5 for all remaining coefficients. So he recommended the Cauchy prior also when there is this particular situation called separation in logistic regression. And let me show you a picture first, which is possibly easier to understand if you haven't seen it before. So suppose we just have one predictor in the model Z here, and Y is the burden response variable. So if you look at this vertical red line here, all the points to its left correspond to Y equals 0, all the points to the right correspond to Y equals 1. So if this happens, we would say that the predictor Z leads to complete separation of the sample points. So it's able to classify all the response variables perfectly in the sample. And Gellman recommended standardizing. So after standardizing, the problem of the separation still remains, as we can see again, if you put a red line here, you can perfectly separate the points into zeros and ones. And the one thing to note here is that the earlier separation line was negative 0.5. If you now put a line here at negative 0.5, that is no longer the separation line, because now there's a 0 to the right of it as well as 1s. So separation remains, but the separation line might change after standardizing. So in general, complete separation is defined this way, which basically means that if there is a linear combination of the predictors that can perfectly classify the response variables into two groups corresponding to y equals 1 and y equals 0, then we have complete separation. And there's another notion of separation called quasi-complete separation, which would basically mean if we had points on the separation line where we can allow some ambiguity in the sense that on this line, on the separation line, quasi-complete separation allows both y equals 0 and y equals 1. So Gelman in this work recommended independent Cauchy priors for complete separation, and in this paper they used the EM algorithm to look at the posterior mode. In this work, we are interested in full Bayesian inference, not just point estimates, and so typically one would use Markov chain Monte Carlo for that for posterior computation. So we are interested in two questions. One is we know that for the Cauchy distribution, the mean does not exist. So we know the prior mean does not exist. In this situation, when there is separation, does the posterior mean exist? This is kind of a natural question, because this is summary statistic. The posterior mean is something that's commonly used. And another question is that logistic regression is kind of different from linear regression in the sense that for real data sets, we don't expect the regression coefficients to be huge. In fact, Gelman himself says that they're often expected to be kind of not bigger than 5. And so do we need something as heavy-tailed as the Cauchy here is another question. So do we have compelling evidence to use the Cauchy? So one reason why Gelman in this, their paper may not have looked at MCMC sampling is it used to be kind of computationally challenging to do MCMC for Bayesian logistic regression as opposed to Bayesian probit regression, which is much easier, until very recently. So in a 2013 paper in JASA, Paulson, Scott, and Windle proposed a very nice and novel data augmentation algorithm with what they call the Folia gamma data augmentation. So they basically come up with this new class of random variables called Folia gamma. And they use normal priors for the regression coefficients. It is not hard to extend their algorithm to student T priors in our work, utilizing the fact that student T can be expressed as scale mixture of normals. So let me show you first the theorem that says when posterior means exist. So this is a very simple situation when there are just two predictors in the model, and suppose there is complete separation in the sample points. Then what this is basically saying is if we have something like this picture where the predictor completely separates the sample points, but 0 is not a separation line. So in this picture we can see if we put a vertical line at 0, either for before standardizing or after standardizing, we have y's that are both 0 and 1 to the left of this, so 0 is not a separation line. So it satisfies the conditions of the theorem, which says then the posterior means would exist for both the coefficients. So here again, p is just 2. And the theorem is kind of more restricted, we think, and this is work in progress, and we're trying to extend it. We think from simulation studies that it actually is more general. The result is more general than p equals 2. And we also think it holds for quasi-complete separation. So this is existence, and the non-existence is easier to show in some sense, at least in more generality. So this says that if there is complete separation or quasi-complete separation, and if we have a predictor for which 0 is a separation line, which is not satisfied in this plot, then the posterior mean would not exist, which may be a strong condition. So in most cases, we possibly have existence of the posterior mean is what it seems. So this is simulated data, and this corresponds to the same picture, the data corresponds to the same picture that I showed you earlier. And here I'm analyzing it with Cauchy priors, and on the top two panels are the running means for beta 1 and beta 2. And we see, so here the theorem says that the posterior mean should exist, and it seems to converge, but very slowly. So even after a million iterations, it still kind of looks wiggly. And the bottom panel, we look at the autocorrelation plots, which seems to show that there's very high autocorrelation and decays very slowly. Here is the same data now analyzed with T priors with 7 degrees of freedom. And we see things start to look better. We still have kind of high autocorrelations here, but decay is much faster now. And here is the analysis with normal priors, which again looks much better. And here is a plot for the posterior samples that I actually suggested, which I think is a great idea. So here, one thing that we see is that the posteriors look very different under the different priors. So here the prior does have an impact on the posterior because there's not much information in the data about these conditions. The maximum likely estimates are infinite in this case. So what we notice for the Cauchy is that the scales are huge here. So the regression coefficients can be in hundreds of the magnitude. This is a little bit more moderate and much smaller. And again, we probably don't expect the regression coefficients to be as huge as that under what we find under the Cauchy. So we think that the Cauchy has too weak information when there's separation in the data. And one might argue that it might still be better predictive performance. So we looked at this data set and several others. And here, this data set came from the UCI repository. So there are different cardiac images, and a cardiologist classifies patients based on these images into normal and abnormal heart conditions. And based on these images, 22 binary features were extracted using a machine learning algorithm. The goal is to see how well these 22 features can predict the cardiologist's diagnosis. And this is a data set where 2 of the predictors lead to quasi-complete separation. This is a case where we still don't have a theoretical result, but we think it's similar to the simulation study where the posterior means exist, but the convergence for the Cauchy prior is very, very slow compared to the other priors. And in terms of, so this data set comes with a training and test sample. So in terms of the correct classification rates, they're very similar across the different priors. We don't see the Cauchy being a lot better than the other 2. In fact, in this case, it's a little worse. But we have looked at other data sets, and they basically look very similar. So we think these results also can be extended to probit regression, and the non-existence result definitely can be the existence result. Again, is a little bit harder to show. And so in this case, we see that the posterior, the tail behavior is very different, and the posterior arising for the Cauchy prior has very heavy tails. And so what Gelman used was a posterior mode that can have very different performance from using the posterior mean. And if one is interested in getting a quick answer, then the TM algorithm that they provide works really fast, so that might be just fine. But for full Bayesian inference using MCMC, or if you want to have variable selection built into that, then we think the Cauchy prior is not probably a good choice as a default. And most likely all the results would also extend to problems where there are multiple